imagine I have one-dimensional data set. In this one-dimensional data set, what I mean by one-dimensional data set is just that I have one feature. So I have few X and O's which are in this one line, okay, on this one feature. If I have X's on one side of my axis and I have O's on the other side of the axis, I can very easily just draw a line in between and separate them. But what if there is a pattern, but I cannot have a line to separate these two from each other? I can still see the pattern, but this pattern is not separable in the dimension that I am at right now. So what I mean is that imagine I have X's on one side and I have X's on the other side and I have O's in the middle. You see, I still see the pattern. O's are in the middle, X's are on the side, but this is not separable in the dimensions that I am at. But imagine if I push and I bend this dimension in this form, right? All of the O's are going to be on top here. All of the X's are going to be on the bottom. So now I can draw a line, and on top of my line is going to be all of my O's, and at the bottom is going to be all of my X's. So what is that bend? What did I do? How do I bend that data, that one-dimensional data, one-feature data? How did I bend it? I took it to another dimension. How do we add dimension in data science and AI? We add a new feature. I have to have another axis, but what is going to be that other axis? I need to be able to bend the line. How do we bend the line? Exponent. So if you take your x to the power of 2, and when you draw it, for example, you have your x here is 1, and then 1 to the power of 1 is going to be 1. So then you have your x at 2, that is going to be 4. And when you draw the line using this new feature that you add to your data set, you are bending the line. And then why is it useful to bend the line? Because now I can find a line that separates O's and X from each other. You're talking about the students in a classroom. The age of the student, the height of the student, the mark that the student gets, each one of these are a dimension that is related to that specific student. And then the more feature that you're adding, the more you're separating these points from each other. So how? Let me explain how. For example, you want to group students in a school. You can group them based on classes, right? So like, for example, you have 100 students and you have 100 students and you have 4 classes. So right now, when you want to group these students, you have 25 in each one of these 4 classes. And then you're going to add another feature, and that is going to be the gender of the students. Then each one of these students are going to belong to a class and are going to have a gender. You're reducing the number of data that is representing each one of these groups. The more dimensions that we are adding to our data set, the more these data are becoming more and more separate, and we have less and less sample to be able to measure. Then I don't want that much dimension. I'm going to take the dimensions down. But imagine you have few data. There are in two-dimensional world, so they have x and y. So you're gonna project that. You're gonna project that in one dimension. So this way, you're losing some information. There are 2 points in the two-dimensional world that are far away from each other in 2 dimensions, but then you project it in 1 dimension and they become very close to each other. So you end up saying, oh, guess what? These 2 data points are very close, but in reality, in the 2D world, these two points are far away from each other. But since you reduce the dimension, you're not able to see that, okay? So this is why they call it curse of dimensionality. because we have problem with it and we have problem without it. But again, as we talked about in case of dimensionality, it's not always a good idea to use polynomials, because every time that you're using a polynomials, when I bent a one-dimensional data set in a two-dimensional data set, I added a complexity to my data set, because right now my one-dimensional data set is two-dimensional. It has the illusion that it is two-dimensional. So what polynomial does is adding more features to your data set. We don't necessarily always need that. There is a way to deal with this, and that is called the kernel trick. So what is a kernel trick? It's going to calculate and tell us the relationship between our data point if we were using a polynomial and we were pushing our data to the higher dimension. It is not actually doing it. It is not pushing our data to the other dimension, and it's not causing complexity to our data set, but it will tell us if you were to push your data set to the next dimension, this is going to be the situations of your data, and this is how they're going to be separated. Imagine you want to figure out how long is it gonna take for a ball to reach the ground if you drop it from, imagine, 10 meters, right? So for the calculation of this time, you can either actually get a ball, go to the height of 10 meters, drop the ball, and calculate how long it takes until the ball reaches the ground, okay? And another way is to use the gravity formula. If you actually use the polynomial in your data set, take your data set to the next dimension and then do the calculation. That is when you are you're getting a ball, going to the 10 meter and drop the ball and then calculate how long it took. But then if you're using the formula, like the gravity formula, that is the kernel trick.